Okay, well, thanks everybody for being here. I was anticipating an audience of about 6 people, so I'm overwhelmed. As most of you know, earthquakes induced by injection activities are associated with modern energy production account for much of the seismic hazard in the U.S., especially east of the Rocky Mountains. The current seismic hazard models that our colleagues in Golden, led by Mark Peterson, update from time to time, intentionally exclude induced earthquakes, including the hazard model for the U.S. that was released in July this year. Clearly, we're ignoring an important component of the hazard, so that, what questions need to be resolved in the course of developing a hazard model for induced earthquakes. As you'll see, it would be very difficult to include induced earthquakes and natural earthquake hazard on the same map, but even producing a separate hazard model for induced earthquakes poses many questions that need to be resolved. So I just want to review in this talk a few of the issues. So I'll start off with 2 slides, just kind of summarizing quickly what goes into the hazard in simple terms from induced and natural earthquakes. But both natural earthquakes and induced earthquakes involve seismic sources. In the case of natural earthquakes, they're either mapped faults or background seismicity from earthquake catalogs. Now, the main point I wanted to draw your attention to is this one. The sources for natural earthquakes are assumed to be stationary, independent of time. Then, so once you've established all these sources, the sources are combined with ground motion prediction equations so that you can calculate the probabilistic seismic hazard at any location. And for natural earthquakes, this is a 2% probability of a ground motion exceeding a given value in a given year. In other words, the maps goes out 50 years into the future, what's going to happen statistically in 50 years. At least once. Now, for seismic hazard from earthquakes induced by fluid injection activities, which a number of other people, including Justin in his talk, Justin Rubinstein in his talk just before the coffee break or beer break, the seismic sources are mostly from wastewater disposal that are a byproduct of oil and gas activity, the modern boom in oil and gas production that we've been experiencing in the U.S. Obviously, faults play an important role because many of the well-located induced earthquakes image faults near the injection site, in many cases faults that were not mapped before. Now, the main point is that the seismic sources, that is the injection activities, are time dependent. Again, Justin in his talk indicated examples of that, and many other people have as well. At any particular well, injection is the wastewater or whatever fluid is being injected is never at a constant rate for various reasons, and regionally, on a large scale, injection activities decline in one region and increase in another depending on economic factors and decisions by regulators and whatnot. In any case, like natural earthquakes, the seismic sources for induced earthquakes would be combined with ground motion prediction equations that are probably not likely to be the same as for natural earthquakes, because I think most of you know already that induced earthquakes, earthquakes due to fluid injection activities, tend to be significantly shallower than natural earthquakes. And so those are used, of course, to calculate the probabilistic seismic hazard. But instead of 50 years, the model that's currently under development by Mark Peterson, Justin Rubinstein, and their colleagues will be for 1 year because of this time-dependent aspect of the seismic sources instead of 50 years. Okay, so the challenges, this top one is a big one, both from the perspective of producing the natural hazard map, because you really have to be confident about which earthquakes you're going to exclude from the map. So you need to know whether or not the earthquake was induced. And it's even more important for producing a hazard model for induced earthquakes so as not to mix in natural earthquakes with it. Okay, the earthquake response to injection is highly variable. Some earthquakes, some injection wells produce no detected earthquakes. Others have a very robust response. Injection activities, as I just mentioned, are moving targets in space and time. And for these reasons, assessment of induced earthquake hazard are very perishable, like fish in your refrigerator. And that's why the map would need to be updated frequently, which is the intention. Okay, so here's one of the biggest challenges, induced or natural. The point of departure would be a report by Scott Davis and Cliff Frohlich in 1993, who gave a number of guidelines for making a decision as to whether earthquakes are induced or natural. I won't review that. I think most of you may be familiar with that already, but I'll just talk about a few recent developments. This one at the bottom, Andrea Llenos reported on earthquake interactions and differences between natural and induced earthquakes on Wednesday afternoon. Many of you were probably at that union session, so I won't go into that. Sue Hough earlier this year published a report on intensity, behavior, and differences between natural and induced earthquakes. I'll review a small part of Sue's study, and then I've been looking into some differences in the relationship between magnitude and fault area. Fault area, as many of you know, is a very robust indicator of earthquake, of at least maximum earthquake magnitude, if you know the area of the fault. Okay, now the example that I'm going to use is arguably the most important and enigmatic earthquake that we who study induced earthquakes have confronted. This is the Prague, Oklahoma earthquake. This figure is from a paper in 2013 by Katie Kiernan and her colleagues. The earthquakes were strike slip. There was a foreshock, magnitude 5 about, which was followed the following day by the main shock, magnitude 5.6 or 5.7. And then the biggest aftershock was several days later, also a magnitude 5. Let's see, the inverted triangles, the gray ones, as well as these light-colored ones, are injection wells. Some of these are exceedingly high volume. The highest volume is the Wilzetta well at the northeast end of the sequence. In any event, just notice that the length of the fault zone as delineated by the earthquake locations is about 18 kilometers. Okay, now what does the intensity tell us that was performed, the intensity analysis by Sue Hough? Okay, this magnitude 5.7 Prague, Oklahoma earthquake, the biggest one, it illustrates what I think is the reason for this discrepancy between the intensity magnitude of 5.1 and the moment magnitude of 5.7, quite a significant difference. These are 8 earthquakes, incidentally, all thought to be induced, at least to some extent, which is why Sue put them all in this figure. She has a corresponding figure for natural earthquakes, and if I showed that figure, you would see that these intensity magnitudes are much the same as the moment magnitudes, but here they're quite different. 2 other earthquakes that I would like to draw your attention are one that Justin Rubinstein and his colleagues published earlier this year in southern for a magnitude 5.3 induced earthquake in southern Colorado. Intensity magnitude, in contrast, was only 4. The Guy, Arkansas earthquake reported by Steve Horton, 4.1 versus 4.8. Okay, so intensity seems to be a fairly robust indicator. The distribution of intensity with distance appears to be a fairly important indicator of a difference between induced earthquakes and natural earthquakes. Okay, what does fault area tell us? Okay, coming back to the Prague, Oklahoma earthquake, this is a slip model developed by Sun and Hartzell, published in GRL earlier this year. The slip distribution shown here and the slip distribution plus the locations, the hypocenters in the earthquake sequence, are enclosed by a rectangle that's 9 kilometers along fault dip, which approximately vertical, and the fault strike. 18 kilometers along strike, 9 along dip, and the fault area is 162 square kilometers. So that is plotted as a function of magnitude, that area on this plot, which shows the distribution for natural earthquakes. Many versions of this plot have been published over the years. This is one of the latest versions by Hanks and Bakken earlier this year. You see that this empirical fit to the data matches the earthquakes quite well, and the scatter is amazingly small. These X's, however, in contrast, are for induced earthquakes: Prague, Oklahoma, the southern Colorado earthquake I just mentioned, Guy, Arkansas, and the Rocky Mountain Arsenal well. They're substantially lower magnitude for a given area than for the natural earthquakes. So again, a very significant difference. Qualitatively, probably due to the similar processes as for the intensity that Sue Hough researched. Okay, so fault area, let me go back. If fault area affects the maximum magnitude for the induced earthquakes, it's a different effect than for natural earthquakes. This is an updated figure the original version of the figure I published earlier this year. The 4 earthquakes that we've just been talking about are, I'm just about done. The Prague, Oklahoma, Raton Basin in southern Colorado, Rocky Mountain Arsenal well, magnitude 4.9, Guy, Arkansas, 4.7. The main point of this is to show that the maximum magnitude is controlled by the injected volume. Injection rate controls the rate of occurrence of these induced earthquakes, as seen here, daily injection rate on the horizontal axis, and the daily number of magnitude 2 and greater earthquakes here. Guy, Arkansas has the highest daily rate up there. Anyway, this is the what serves as the conclusion slide, but it's more than conclusions. As I said, a one-year hazard model is being developed and probably will be released this coming year. It will be updated frequently. Let's see. These are two of the challenges: what ground motion prediction equation to use, what's really controlling the maximum magnitude. I think it's injection. Other people have different ideas about what might control it. I won't get into the policy implications because this is a science meeting, but there are plenty, I can assure you. Thank you.
Thank you. So
Okay.
we have time for one short question.
Yeah, I'm just wondering, given that injection data is often only released 6 or even 12 months after the fact, do you think it's possible to stay ahead of the seismicity hazard with only a 1-year hazard model?
Yeah, thanks for raising that. Oh, okay. Yeah, the question is, the injection data are often only released many months after the actual injection takes place at any given well, which is true, definitely true. This is a serious problem, and it shouldn't be in this day and age. And obviously, we scientists would like the injection data to be available almost immediately, so we can really address these issues. And of course, regulators would like to have access to those data as well. So it's a very good point. I hope the situation will improve.
Thank you.